Okay, good morning, guys. 5.3, we're going to finish this up, our rules of integration. I didn't like how I presented my 5.3 average value theorem last Friday, so I'm going to try to buzz through it again. Hopefully I go through it a little bit quicker. But basically, I got my graph f of x drawn there. And they want you to find the average value of f of x on the interval from a to b. So what is that really asking me to do? Well, that wants me to find the average y value from a to b. Well, let's think about that for a second, because how many y values exist between a and b? Or how many y values theoretically exist between 1 and 2, or 0.2 and 0.3? There's an infinite number of values in there, okay? I understand you know how to find an average of something. You add up how many there are, right? And then divide by the number you added up. But if I'm trying to find all these y values in here, and I mean, I can't even draw them all in there, and if I start beginning to end or whatever, it really doesn't matter. There's an infinite number of y values in there, okay? So how are we going to do this? Well, I can just give it to you, yes. However, I want to connect it to something. I want to connect it to something that you already know. So we're going to consider the specific situation that I talked about on Friday, which is going to connect this average value idea to us. And the thought is, how have we calculated our average velocity, which is our a-rock on the interval of time from A to B? Well, how did we do that every time? What did we do? We said our average velocity. Well, what does that equal? Average velocity is our change in distance divided by our change in time, or our change in displacement divided by our change in time, where my change in distance can actually be called, like I just said, displacement, which is divided by my change in time, okay? Well, displacement, how do we get that displacement? Well, all displacement is where are you in the beginning compared to where are you in the end. You subtract where you ended up from where you began. That's your displacement, right? And let's say, okay, S of t, because they like S of t is going to equal my position function. My position function. So that is what they typically call our position function in calculus, is S of t. Well, how do we find it? Well, we find our average velocity on the interval from A to B. How did we find that? Well, we took our change in position. We took S of B, our position at B, minus our position at A, and we divided that by B minus A. And what did that give us? That gave me my change in position, or my displacement, divided by my change in time. And I know you're sitting here saying, okay, well, what's the big deal here? Well, the big deal here is when I come to this next page, okay, and this is a very specific situation. We are asking to find, basically, we are now being asked to find, let me put it that way, move all this stuff down just a skosh. We are now being asked to find, what the heck are we asking me? I want to find, or to calculate, the average velocity, except I'm using my velocity curve on A to B. Okay, before when we found average velocity, we needed our position function, right? We took our change in position and we divided it by change in time. That gave us our velocity. But now we're kind of changing the game here. Okay, we're changing the game because now I have my velocity curve, And I want to be able to find my average velocity in this situation from A to B. Well, it doesn't matter. My average velocity, it still hasn't changed. It's still my change in displacement divided by my change in time, right? Where my change in time, it's still my B minus A value. But the question is, how the heck am I coming up with my change in displacement? Where is my change in displacement coming from my velocity curve? Okay, well, let's think about this now. Where is it coming from? If this is truly my velocity curve, my units over here, velocity, say feet per second, and my x-axis is going to be in seconds because that's going to be my t-axis. Well, what happens? How can I find my change of position? Well, what am I doing? I'm accumulating my area, aren't I? And if I accumulate my area, I'm multiplying my units, where feet per second times second gives me feet. So how am I going to find my displacement using my velocity? Well, the simple answer is my change in displacement is now going to be my integral from A to B of v of t dt. Okay, it's an integral because if I'm accumulating velocity, that accumulation of velocity is going to give me my position. And then I should have I'm having my change in d. So this is where this whole average velocity business is coming from. So now, if I can get my change in position with my velocity curve, because now my velocity curve is simply going to equal, now I'm the integral from A to B of v of t dt divided by my change in time. That's still b minus a, all right? Well, how do we get that? Well, if we rewrite this just a skosh, this is actually going to equal 1 over b minus a times the integral from A to B of v of t dt, where I can see here, and if I think about this in units, okay, right here, 1 divided by b minus a, that's going to give me my seconds, right? That's my seconds, times what? Actually, it's not going to give me that. It's going to give me 1 over seconds, excuse me. It's going to give me 1 over seconds because I got a constant unit of time on top. And then if I integrate my velocity, well, if I accumulate my velocity, what that is going to give me feet over 1. So I'm going to end up getting out of here feet per second, which is my average velocity. Okay? Well, that's our connection. So let's turn the page here, and then at the end, we're going to apply this concept to any function that we want. All right? So let's look at our average velocity here now, okay? So now we're calculating our average velocity, and now I just kind of bombed through it pretty quick. We're going to have 2 ways to do this. We can use our position curve, and remember we're calling our position curve S of t, and how do we find that? Well, we find the average value of S of t on A from A to B. So my velocity average using my position curve is simply my position at point B minus my position at point A divided by my time change of B minus A. This gives me my change in displacement, or my displacement, my change in distance divided by my change in time. Well, now we're just learning we can use our velocity curve as well. Okay? So our velocity curve, we're going to use v of t on the interval from A to B. Well, how the heck can we do that? Well, our velocity average here is now going to be 1 over b minus a times the integral from A to B of v of t dt. Okay? And if I'm accumulating my velocity, what do I get? I get position. And the really cool thing about the math here is we can scroll down and we kind of prove this is the exact same thing, because if I'm coming across here and I take 1 over b minus a, that's going to be times the derivative of this. What is the antiderivative of velocity? Well, we know the connection between position, velocity, and acceleration. If I take the derivative of position, I get velocity. So if I take the antiderivative of velocity, I get my position curve, and I can evaluate that from A to B, which that's going to give me what? My 1 over b minus a, and when I use the fundamental theorem of calculus, I'm going to get s of b minus s of a. And if I look at this, if I'm multiplying a fraction times that s of b minus s of a, what do I get? I get 1. I don't get 1, come on. What do I get? I get s of b minus s of a divided by b minus a. And what do I notice here? I get the same thing. They're the exact same thing for my average velocity, okay? Now, I don't know about you, but that's kind of cool, because now we can find our average velocity using position or our velocity curve, okay? Same way we can find our average acceleration using our velocity curve, because we did this. This is where people got hung up too, right? We can use velocity, or we can use v of t on the interval from A to B to find our average acceleration. Or now we can also, we'll be able to use our acceleration curve or function A of t on A to B to find our average velocity. Okay, well, think about this. If I'm using my velocity curve, okay, my acceleration average equals what? Well, change in my acceleration average, or my average acceleration, well, that's change in velocity divided by change in time, right? That's like my feet per second, which gives me my feet per second squared when I come across, right? Well, how do I get that? My acceleration average is going to equal, well, my change in velocity right there. If I'm using my velocity curve, well, that's just my velocity at point B minus my velocity at point A divided by my B minus A. Excuse me, that's using my velocity curve. But what if I use acceleration? Well, my acceleration average now, if I'm using the acceleration curve, that's going to be 1 over B minus A times my integral from A to B of A of t dt, because think about it, the derivative of velocity is acceleration. So if I cruised and bruised along here, and I found my antiderivative of acceleration, okay, my antiderivative of acceleration, hey, that's velocity. We know that, evaluated from A to B. So I kind of come through here and I say, oh, it's 1 over B minus A times my fundamental theorem of calculus evaluated my velocity at point B minus my velocity at point A. And if I multiply that, what do I get? I just get my velocity at point B minus my velocity at point A divided by B minus A. And what do I see? I see again, they are the same thing. Okay, so I can find my average acceleration using my velocity curve or my acceleration curve. The same way I can find my average velocity using my position curve or my velocity curve. Well, in general, what does this mean? It means I got to go to the next slide. In general, this means the average velocity of f on A to B. So I have my little function here of f from A to B, and this is f of x. I can find my average height in there. My average height, f average, is going to be called f of c, and I'll tell you why here in a minute. I'm going to get that by taking 1 divided by the width of my interval times the integral, or the area, of from a to b of f of x dx. And what this average value theorem kind of does is it averages the y values of the function on a to b. Well, and remember, this y value, this is the height of my function. And really what it does, if I integrate from a to b, okay, it's given me this area bounded between the curve. And it doesn't matter if that area is positive or if that area is negative, right? And they're talking about this f of c value. What this average value theorem is actually doing is when I find the average y value height in here, okay, what I can do is it's positioning this whole area that we have here and some of it, and it's breaking it all into one rectangle where I can take, here's that f of c value, okay, so there's some average height in here, and I'm going to call it right here. I can't call it that first one because it's not on my curve. So let's say, hey, I could use this c value right here. That's going to be my c. That's going to give me my average height of all those heights between a and b. So if I took that f of c value, and I took that f of c value times, because remember that's a y value, times my b minus a value, that's my x. If I take that y times that x, I get the exact same area that I have underneath the curve. It's just placing it into one rectangle, okay? So that's where, if I actually look at this whole average velocity business, this f of c, it's called, and it's just it's a rogue c value somewhere inside a and b, that f of c equals 1 over b minus a times the integral from a to b of f of x dx. Well, if I use a little bit of math here, okay, and if I multiply this whole side of the fraction by b minus a, well, that means I have to multiply this side times b minus a. That means if I take f of c times that width interval of b minus a, it actually equals the integral from a to b of f of x dx. If I average all those heights, when I find the average height on my interval from a to b, that magical height value times the overall width will also give me the area under the curve, is what it's really placing out for us. Okay, so let's take this one once. Let's find the average value of f of x on the interval from -1 to 3 for f of x equals x cubed minus 1. And then I'm going to kind of really point out what we're getting here, if you haven't grabbed it yet. So, well, we're going to find that f of c value, which is really the average of f, okay? Or actually, I'm going to write those back the other way. I don't like writing it that way. If I want to find my f average, well, that's really that magical x value, c we're going to call it, that c value, c is somewhere in between -1 and 3. Okay, that's actually going to come from 1 over b minus a times the integral from a to b of f of x dx. Okay, so I'm going to try to get this. So we're going to say f of c is going to equal 1 over 3 minus -1, because there's my a, there's my b, times the integral from -1 to 3, and f of x is x cubed minus 1 dx. Okay, so what are we getting here? Well, the fundamental theorem of calculus, this gives me 1 over 4 times, I know my antiderivative of that, that's going to be x to the 4th times 1/4 to get rid of that, minus x, and we need to evaluate that from -1 to 3. Okay? Well, notice this 1/4 is multiplied after the integral is there. So I'm going to take my 1/4
times, now I have my b minus a that I have to evaluate here. Well, when I take 3 and I put it in there, 3 to the 4th power is really 3 squared, right? So it's really 1/4. Why would I write it that way? It's really 81 over 4, right? Because 3 to the 4th power is 81. That really gives me 81/4 minus 3. And then I plug my -1 in there. Well, that's going to give me -1 to the 4th is positive, so that gives me 1/4. And then minus -1 is +1. And we want to be sensible the way we do this, ladies and gentlemen, so I'm not going to distribute this 4th yet. And I'm going to say we're really looking at 81/4 minus 3 minus 1/4 minus 1. So if we're sensible about this, we're going to put our fractions together first before we need to do anything, because as I'm cruising through here, I'm going to see this is going to equal 1/4 times what? Well, 81/4 minus 1/4, that's 80/4, and 80/4, that's really just 20, isn't it? And then -3 minus 1 is -4, so this is really going to give me 1/4 times 16, and what is 1/4 times 16? That equals 4. So we just found f of c equals 4, okay? My average height is going to be 4. When my average height is 4, notice we haven't found what x value gives me that 4, but I know my average height is 4. So here's what this is going to look like. So I got it graphed in my calculator here for you, and I graphed f of x equals x cubed minus 1. And what this is actually doing is it's taking this whole area between -1 to 3. So you don't have to know how to do this. I'm just laying you the picture in here. And if I analyze this graph as an integral from -1 to 3, I can see my area here is 16, right? My area is 16, so it's taking this negative area and this positive area. So what that means is when I found out in my problem here, when I found out f of c equals 4, well, that means up here at 1, 2, 3, 4, I can make this calibration's off. I can make one big rectangle on here over my entire interval, and that height value of 4, this red area that I just found, okay, it's taking all the area underneath the curve, and it's making it the same area because I can see f of c. I know that height is 4, and granted, it's looking a little weird, but that width is going to be 3 minus -1, which is 4. What is 4 times 4? It's 16. So it's finding my average height across that interval, that when I multiply that height times my overall width, it's going to give me the area under the curve. Okay, it's finding the average height, the average temperature under the curve, the average velocity under the curve. Because remember, if it's my velocity curve, there's my average, there's my height average, and it would be a y value, so it would be velocity, it would be acceleration, it would be something like that. So that's what this average velocity or average f average is finding for us, okay? Well, your next question is probably, well, that's all great, okay? How are we going to use it? Well, we're going to use it on one more application problem here. And notice that was a non-calculator problem that I just did. And let's say if v of t equals t cubed minus 3t squared minus t plus 8 in feet per second, find the average velocity on the interval of time from 0 to 5. And they're saying, hey, this is a calculator active problem. Well, that's really nice, okay? That's great because I know my calculator will do all this math for me. Well, if this is my velocity curve, okay, and I need my average velocity, I know if I accumulate my velocity from 0 to 5 of v of t dt. Okay, and I'm just going to write v of t dt because this is a calculator problem, number one. And all they're looking for is you to write your calculus, and you don't have to waste your time writing this whole function in there. You're welcome to if you want. But just think about this. If I accumulate this velocity, this is going to give me feet, right? And so how am I going to get the average? Well, I need to multiply that by 1 over 5 minus 0. That's going to give me my velocity average. And I can see that because this is going to multiply this output with the units of 1 over seconds. And when I multiply them, I get my feet per second coming out, which is velocity. Okay? It is velocity. So that's how we're going to get it. So all we need to do now is we need to plug this into our calculator. Now, if this were a free response, okay, they don't just want the answer. Guys, please, a word to the wise. Contrary to popular belief, your work means a lot, okay? Your work means, and I shouldn't have an equals there, this, my velocity average equals 1 over 5 minus 0. Your work means a lot, meaning on the AP test, they're not concerned, well, they're concerned about the answer, but they're concerned about seeing your calculus. This writing right here, this is calculus. That's what they want to see, not just the answer. If this were a free response question, just writing that integral is worth a point for you to get. The next point over here, the next point would be the answer appropriately rounded to however they want it, okay? So what we're going to do is we are going to go to our calculator and we're going to find that average velocity, and I got it plugged in already. All you got to do is multiply 1/5, this is my 1 over 5 minus 0, times the cumulated, or times the integral from 0 to 5 of my velocity function. There's my velocity function, but because I didn't take the time to define it as f of x or anything in there, because this is the only time I was going to use it, now on my calculator I actually have to type the function in. And I could have typed it in as x cubed minus 3x squared minus x plus 8, as long as I said dx at the end. Okay, then I'm going to hit enter, and my answer is 47/4. So I'd come to the back, and I would say, hey, my average velocity is 47/4. That's not good enough. It's not good enough to put that because please don't forget units. If you don't have your units on there, you're going to be wrong. Okay, feet per second. Some people are going to say, well, I'm not in exact value mode. Would it be okay if I put 11.75? Yes, you could, as long as you put feet per second after it, okay? So bottom line, if this were what I'm trying to communicate very strongly right here, is if that's all you wrote in that section of the test, you will lose that point. They'll give you the one for the end, but they're going to lose the point. You're going to lose the point for the calculus. All right. So how else are we going to use it? Well, this is back in 1998. Ooh, this is a nice one. This is a nice one because it was a calculator active problem. Well, it's because it's a nasty one to integrate. Okay, and the temperature outside a house during a 24-hour period is given by f of t. So this is my temperature function. That's my temperature function for the outside, where f of t is measured in degrees Fahrenheit and t is measured in hours. Sketch a graph of f of t on the grid below. Would they do that? Yes, they would do that. Well, think about this. Got to go all the way back to your pre-calc. We were where you were in there, and you're gonna look at this, and hopefully you're looking at this, and you're identifying with this 80, and you're like, that's a vertical shift up 80 units. So I got a vertical shift. This minus, or excuse me, I'm not throwing that any minus in there. I want my eraser. I'm going to say we're cruising along here. We're going to focus on that 10, so we know the amplitude is 10. And remember, we also had to calculate the period. Remember, the period was always 2 pi divided by b. And if I took 2 pi, and my b value here is pi over 12, I can see the period is 2 pi over 1 times 12 over pi, and I can see those cancel out, and I can get 24. See how they're making you graph one phase of your graph from 0 to 24. And then how I always used to teach this is I would divide that by 4 to get my x scale, I called it. Notice they put that in terms of 6 for you right away. So I know my period equals 24. And I cannot forget about this little symbol right there, that's subtraction. What does that mean? That means it's a flipped cosine, okay? It reflects the x-axis. So, well, let's think about this. Originally, we would have our equilibrium line, or your midline as you called it in there, and then you would go and you would graph your 5 points on there. And on the 5 points, typically your cosine started up here, right? But because of that negative, it starts on the bottom, and then we went to our x-axis, then we go to our maximum, then back to our x-axis, and then to the bottom, and then we just connected that with the best smooth curve we could. And boom, shakalaka, we got a point. And also, because it's calculator active, it would probably be pretty intelligent to type this little bugger into your calculator. And I typed it, stop. I typed it into my calculator right there. And then when I hit enter, I'm like, well, crumb, I don't see it. Well, that's because we need to change our windows. Well, if I changed my windows, it would probably be very intelligent to change your windows exactly as the graph they have you do. So I would go from 0 to 24 with a scale of 6. And if you see, we started at 60, and then it went to 100, and the scale was 10, and I hit OK, it's going to bring that right back to the graph as you see that. And you're like, I don't like that. The one on the test has got all these cute little graph lines. Well, I can put these graph lines on there. If you go to Menu, View, and you go Grid, and you show Line Grid, boom, there they are. This thing usually annoys me, so I take that off, so I'm just looking at my graph. No, I don't. No, I don't. I gotta pause. Okay, I got it back. So you can kind of compare, just like I said, so you can compare your graph to what is in your calculator. And there's another nice thing, because as you turn the page here, we have already defined our function in our calculator, number 1. So as we come to this next one, they're saying, oh, now we got to do some stuff on here. Find the average temperature to the nearest degree Fahrenheit. So you would be able to look at your graph. So what I did is I copied my page here, and I'm going to paste this bugger on here, and I'm going to squirrel it right into the spot over the top of what they have for me here. Try to get it to fit there. And I'm just going to leave mine there. Make mine a little bit bigger so I can see that. Okay. I'm just going to be looking at my graph. And they want us to find the average temperature to the nearest degree Fahrenheit between T equals 6 and T equals 14. Well, here is T equals 6, and then this was 12, and this was 18, and that was 24, so T equals 14 is going to be somewhere right in there. I want to find my average degree, find the average temperature. We just did that, finding average velocity using the velocity curve. Now we can find the average temperature using the temperature function. So we can find my F average, my average temperature, by taking 1 over B minus A, right? There's my 14, times my integral from from 6 to 14, from 6 to 14 of big F of t dt, and I'm just calling it big F of t dt because that's how they defined it to me back here. So rather than write that whole function again, okay, I'm just going to identify it at every problem on the test that I need it as f of t when I go to my calculator. Remember, this is a calculator problem. So they're looking to see your calculus. We have just earned 1 point. Well, what is my average value from there? Well, then I just come back and I grab my calculator. Now, I'm going to come back here, and I'm going to show you. Here's my graph, right? That tab. That graph is in F2 of x, because I graphed a different one in there. I've defined my entire function in my graph as F2 of x, okay? So when I come back here to my page, now I can calculate that average value by saying control divide, and I'm going to take 1 over 14 minus 6 tab times my integral 43 from 6 to 14 of, now I don't want to type that whole ugly 80, what is it? 80 minus 10 cosine pi t over 12. I can, but it's already defined in my calculator as f2 of x, is it not? So my calculator is going to reach in and it's going to grab it. So if I want to integrate find my average temperature from 6 to 14, I will accumulate my temperature hours from 6 to 14, and I will multiply it by the hours in front, and it's going to give me my temperature of, come on. It's going to give me, I don't want to write that as my answer, 87.162. 87.162. However, 87.162 to the nearest degree Fahrenheit, so we're going to say this is approximately equal to, what was it? 87 degrees Fahrenheit. We just got 2 more points, one there, and my calculator did it all. Okay, moving on. An air conditioner cooled the house whenever the outside temperature was above 78 degrees Fahrenheit. For what values of T was the air conditioner cooling the house? There's absolutely no calculus involved in this problem, okay? There's none. So all they're doing is they're saying, hey, this is like an Algebra 2 problem. Here's my curve. This is 60, 70, 80, 90, 100, okay? The air conditioner kicked on whenever the temperature was, what? At or above 78 degrees Fahrenheit. So they're saying, okay, for what values of T, what is that value? What is that value? At what values of T was the air conditioner cooling the house? There's 2 ways to skin a cat, okay? What we can do is we're going to come back to our calculator, and we're going to come back to our graph. This is the easiest way, and we want to see another graph on there, don't we? We want to see 78 degrees. So it's going to place my 78 degree line on there, and I know that when I say menu, analyze my graph, intersection, from there, there's 1, menu, analyze my graph, intersection, I'm going to go from there to there, so I can see these. Now these were not to be rounded because they're times, right? So that would be 5.231. Yes, remember, gotta look, round, that's 5.231 and 18.769. So, to answer our question, we will come back and we will say, oh, this is going to be for t greater than or equal to, what was my first one? 5.231, but less than or equal to, because it says at or above, so the equal to needs to be there, 18.769. Now that's not the only way to get it, okay? This is a good chance here. And sorry this is going to be a longer one, but I can also say, well, what if I forgot to do the intersection of my graph and I wanted to come back to my calculator? Well, again, we could use solver. We could say menu, algebra, solve, and we could solve, because it's already in there, f2 of x equal to 78, right? And our solver is going to give us that, but we got to say, please, comma, solve for x, right? Enter, and I'm getting some wonkiness in here again, so I better control enter. Whoa, what's going on here? Oh, that's right. Trig functions are what they call periodic functions, and there's an infinite number of solutions. Okay, it's finding all the intersections of this entire curve from negative infinity to positive infinity. So, what we do when you do this, I said do, you need to put a parameter on your function. So you're going to say solve, your function equals whatever comma x, and then you're going to come here and you're going to say control equal, and you're going to use the such that bar, such that, and we're going to type in our parameters such that 0 is less than or equal to x, which is less than or equal to 24, and then we're going to do there they are. And as soon as I put my parameters in there, it's only going to give me the solutions on that particular interval, okay? That's using your solver with a trig function. You got to give it the old such that bar right there, and then put your parameters in, okay? So, get out of there. I don't know why that's red. So then, we're going to come back to the last problem. And then, the final one here says, the cost of cooling the house accumulates at a rate, it accumulates at a rate of 5 cents per hour for each degree outside the temperature. For each degree, the outside temperature exceeds 78 degrees. Well, why is that? Well, because the air conditioner doesn't turn on until it's 78 degrees. What was the total cost to the nearest cent to cool the house for this 24-hour period? Okay, well, what are we looking for? We are looking for the only time the temperature was above 78 degrees is the only time we have cooling costs, isn't it? So are we or are we not looking for this area right up here? And that's the only area we're looking for up there. And you got to be super careful now, right? Because if I typed in 0.05 times my integral from between these two intersection points, which are here and here, okay, meaning 5.231 all the way up to, what was it, 18.769 of f of t dt, right? F of t dt. What that's going to do, think about, what is this area going to be? Okay? Think about what an integral represents. It's the area of the curve. It's the area bounded between the curve and the what? The x-axis. Okay? So if I actually did that, and I came back here to my graph, and I changed my window a second, watch what's happening here. If I integrate my window settings and I take this all the way down, delete to 0, and I'm shifting, so now I'm seeing my x-axis. If I tell my calculator to accumulate my area from point, and I'm gonna put this round in it, 5.231. What's going on here? That's why. Back. So when I do my menu, graph, analyze my graph, integral, I need to pick the graph, the red graph, and if I say my lower bound is 5.231, and I say it's all the way up to 18.769, it's going to give me the entire area underneath that curve. And remember, the only area I want is when I'm above 78 degrees. Okay? That's the only area I want. So there's two ways to find this, okay? I can find that area, first and foremost, by shifting my graph down to the x-axis. Meaning, I can say tab, and I can say tab, and I can say tab, up, up. Let's say I shift it down 78 degrees, or 78 units now, so that I'm finding just the area above the x-axis. Notice it substantially changed it because it got rid of all this 78 times my interval width. Okay? So it got rid of all of that stuff. What are you trying to tell me? Hopefully you're picking up what I'm putting down, and I'm just saying there's two ways to skin a cat. Well, how do we want to skin the cat? Well, live or dead? Not really. But we have two ways to do this. The two ways I'm talking about is we can take, okay, our cost is going to equal my 0.05 cents times my integral. If I want to do it the easy way, I'm going to go from 5.231 to 18.769 of f of t shifted down 78 units dt. You mean I can just shift my graph down by subtracting outside of my function and it's going to shift it down? That's what I'm telling you. It's that easy. Or I can say my cost is going to equal 0.05 times the integral from 5.231 to 18.769 of f of t dt, but then I have to subtract the whole area that was 78 units high times the difference in my interval, which would have been 18.769 minus 5.231. See, here's my y, here's my x, here's the area I'm subtracting from the total area. Okay? And I want to go there, and I'm going to get my total area coming out. But I would have to bracket my 0.05 off. Easiest one is this top one, shifting it down. Then all you do is you come back to your calculator. Oh, that's right, but now it's shifted down, so if I left it where it was, meaning I don't want to shift it down if I'm going to shift it in my function, okay? Oh, there it is, as the whole thing's up. Now if I came back here, now I'm going to say 0.05 times my integral from 5.231 to 18.769 of, I called it f2 of x, and I want to shift it down 78 units dx. I did it again. Enter. I want to approximate. And how much did it cost? Do not round this answer to 3. It's money. $5.10, right? Now I come back here and I say equals 5.10. And that is the end of the world. Type this guy in the way it is, you know it's going to equal $5.10, okay? That's how you're going to use the average value theorem on the AP test in May. Hey, the only reason this one's longer, guys, is because of the beginning there, going over how I didn't like how I presented it on Friday with the average value theorem. I hope I did a better job today. And thanks for playing math, and have a great rest of your day. Talk to you tomorrow.